So if we look at old final exams, a lot of applications of this section, let's see if I can find the one I'm thinking about. This would be the application of this section. To have you go through on a problem and do all the steps is very, 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 very time consuming. So more so I'm going to say, can you graph a function given all these data, all this information? So I don't know why Adobe is freaking out on us, but if I give you all this information, I've given you information about the graph, can you graph it? So today, before we're not going to have any of this, we're going to have to find it ourselves, which is really the majority of the work. After we have everything, throwing it into the function, we need to know how to draw a concave up increasing function or a concave down increasing function. Do the first derivative test or the second derivative test to see if it's going to be a maximum point or a minimum point. Find the x-intercepts, find the y-intercepts, things like that.
Is that
Question?
kind of like your lines?
Yeah, it would be. It's just the date, right? So I know the sign of f of x. Here are my breakdown in my intervals. It's positive here, or it's negative here, positive, negative, negative. So I know my function is decreasing, increasing, decreasing, decreasing. It's decreasing here in concave down, right? So I need to be able to draw a decreasing concave down function. So it's not going to hold water, right? Or a decreasing concave up function would hold water, but it's still decreasing. So I have those kind of four options depending on my setup. Here my function's increasing and it's concave down. So it's increasing and concave down. So it looks something like this. It's decreasing and concave down. It's decreasing but concave up. So you're going to have to sketch this graph to get it to satisfy all these conditions. Above that, the horizontal asymptote, when I'm going to infinity is 1. When I'm going to minus infinity, it has to go to 3. The value of the function at 1 is 4. So I need to make sure I go through the point x equals 1, y equals 4, things like that. And then the layout of the graph would be there, and then you just need to connect the curves, satisfying concavity and increasing and decreasing. But we're going to come from the start, from the beginning of it, we have to be able to find all that on our own. So another application in this section would to be find maximum and minimum points, find horizontal tangents, find vertical tangents, find inflection points, things like that. So be able to label them as inflection points and be able to get information from the graph without necessarily going through all the steps and graphing it. So knowing how to find a maximum point, knowing how to find concavity, knowing how to find where the function's increasing, where the function's decreasing, things like that. All right, so before we start in 4.3, I want to finish up where we were at in 4.2. So let's see where we were at last time. So last time we just defined the first derivative test and the second derivative test, but we didn't get to any examples, right? So we talked about the first derivative test. The second derivative test is still going to test if a critical point is a maximum or a minimum. If I take the second derivative, plug in the critical point and it's positive, I mean concave up, so I have a minimum. If I plug in the critical point and I get a negative value for the second derivative, I'm concave down in that interval, so that maximum point has to be that critical point has to be a maximum point. So don't try to necessarily, memorize these theorems without thinking about it. You can think, if I have a picture that looks like this, that means I have a positive slope and then I have a negative slope. That's a maximum point. If I have a negative slope, then a positive slope, that's a minimum point. Okay, so let's continue. We'll just say, what was this, 4.2, day 2. And let's look at some examples. Examples from 4.2. So this is number 36. So it asks you to find max/minimum points using both the first and second derivative test. So this is just going to illustrate the first derivative test does the same thing as the second derivative test. So you should get the same conclusion there. You would never have to do both of them on an exam or a quiz. This is just showing you could do one or the other and get the same answer. Honestly, the second derivative test is not as conclusive as the first derivative test. First derivative test is always going to work out. It's always going to give you information. The second derivative test will come in handy when we talk about application problems. So if you get a critical point, you might have to do the second derivative to confirm if it's a maximum or a minimum, or do the first derivative test. And we'll see some applications of that later on in Chapter 4. So looking at the function here, x minus 3 times the quantity e to the x. So a little bit about e to the x. Usually a function like this shows up on the final exam to know that e to the x never equals 0 and it's always positive, and know how to deal with that. So we're going to have to factor it out. So if I take the derivative here, what do I get? E to the x plus x minus 3 e to the x, right? The derivative of x minus 3 is 1. Hold e to the x plus the derivative of e to the x, which is e to the x, hold x minus 3. You could have also gone about it as writing x e to the x minus 3 e to the x. You'll get the same thing, differentiating it. So now the first derivative test, I want to set this equal to 0. I need to factor out that e to the x so I can solve when that equals 0. E to the x never equals 0. So if I factor out e to the x, I'm left with 1 plus x minus 3 equals 0. Well, e to the x never equals 0, so 1 minus 2 has to equal 0, right? When does x minus 2 equal 0? At x equals 2, right? So this is a critical point. We also know it's a relative extremum. So to figure out if it's a relative maximum or relative minimum, I need to do the first derivative test or the second derivative test. So let's look at the first derivative test. The first derivative test is where I test the sign of the first derivative. So if I plug in a number on the left side of 2, let's plug in 0. What do I get? What is e to the 0? 1. 1 minus 3 would be negative, right? So this is going to be negative. And let's say I plug in 5. E to the 5th is positive. More so, e to the x is always positive. Never can equal 0. So I really don't even have to worry about that term. I only have to worry about the inside. If I plug in 5, I have 6 minus 3, which would be positive 3, right? So it's positive. So here, the first derivative test, what would my conclusion be here? It's a minimum, right? I have a negative slope on this side and a positive slope on this side, so it's a minimum. Minimum point. If I wanted to apply the second derivative test, the second derivative would say, take the second derivative, plug in 2, and what am I expecting the second derivative to be? Negative or positive? We already know it's a minimum. So we're expecting the second derivative to be positive? Exactly, concave up, right? Concave up gives you a minimum. Positive is concave up, it holds water, so it gives you a minimum. So let's go about doing that. So now I want to take the second derivative. So I get e to the x plus e to the x plus x minus 3 e to the x. Okay. So if I clean this up a little bit, what do I have? 2 e to the x plus x minus 3 e to the x. So if I take the second derivative and plug in 2, because 2 is my critical point, I get 2 e to the 2 plus minus 1 e to the 2, which gives me a positive e to the 2. Right? E to the 2 is always positive. So therefore, I'm concave up.
How did you get 2 e to the 2?
Here. So I plugged in I have 2 e to the x. When I plug in 2, I get 2 e to the 2. I'm plugging in 2 for x of this function.
She's asking why you're using 2.
I just took e to the x plus e to the x.
Oh, okay.
Sorry about that, yeah. Question?
You just plug in 2 into the second derivative test because that's the critical point.
Yeah, 2 is the critical point. So if I plug it into the second derivative, it's saying if it's positive, means I'm concave up, I have a minimum. If it's negative, I have to be concave down on that interval. I still know it's a critical point by, it's a stationary point because the first derivative equals 0 there. So it's a critical point. And that critical point on a concave up interval would be a minimum. The critical point on a concave down interval is a maximum. But this doesn't say anything, this has nothing to do with inflection points. Inflection point would be when the second derivative equals 0, right? So we could go about looking at that. Let's see. Notes at. So I could say, if I wanted to find the inflection points, which would be a different problem, or maybe in the same problem, the inflection points is when the second derivative of the function equals 0. That has nothing to do with the second derivative test. Second derivative test has to be about classifying the critical points. Critical points are when the first derivative equals 0. So if I take that first derivative, find the zeros, if I plug the zeros into the second derivative, and it's positive or negative, it will tell me if it's a maximum or a minimum. Okay, so in the inflection points here, so I already know that the second derivative function is 2 e to the x plus x minus 3 e to the x. If I want to solve for when that equals 0, I factor out the e to the x, and I get 2 plus x minus 3 equals 0. So that means x minus 1 equals 0, so that means x has to equal 1. So if I look at the second derivative, if I plug in a negative number, say I plug in 0, because 0 is on the left side of this, I get 2 minus 3, which would be negative, right? So this is negative and this is positive. This is concave down. This is concave up. X equals 2 is in this interval, so it's concave up, so it has to be a minimum. But if I was to graph it, I need to make sure that I'm concave down in this interval and I'm concave up in this interval. So x equals 1 is an inflection point. When the second derivative is negative, is that making sense? It's concave down on that interval, which would be a maximum point. When the second derivative is negative, I'm concave down.
What about if it's fourth derivative? If it's negative?
What?
If it's fourth derivative.
If the first derivative is negative, that just means your function's decreasing.
When we are taking the second derivative, that's when we are looking at the concave down.
If you're looking at something like this on the second derivative, yeah, you're looking at concavity. And if you look at x equals 2, that's on an interval when I'm concave up. I know x equals 2 is a critical point, and it's on an interval where your concave up means you're a minimum point. If your critical point was on an interval when you're concave down, your critical point would then be a maximum point. So the first derivative test and the second derivative test is all about classifying critical points as maximums or minimums. This approach to the second derivative tells you where the function's concave up and concave down. So once you get all this information, you can graph it.
The part where you have the second derivative equals e to the
This
red button.
here,
Yeah.
yeah.
How did you get to figure out that that was concave up?
Because it's positive.
And where did the negative one go?
Well, because I take 2, e to the 2 minus e to the 2. So e to the 2 is just a number, and I have 2 minus 1 of that number. which would just be positive 1.
That makes sense.
Does that make sense? Yeah. So if I have 2 minus 1 of e squared, which would be 1e squared. And 1e squared is always positive. E to the any number is always positive. So negative e to a number is negative. Any other questions on that? So let's look how we're going to apply it in 4.3. So 4.3 is all about graphing functions and graphing rational functions. So this is part 3 of our analysis of functions. We're going to look at cusp and vertical tangents. We probably won't get to them today, though. So we're going to focus on graphing a rational function. And a rational function would be the form p of x over q of x, right? We've seen that before. More so, p of x and q of x are going to have any common factor. So we want to make sure we factor them and make sure they have no common factors. Okay, so your book goes through all these steps, like step 1, check this, step 2, check this, step 3, check this. You don't have to do them in order. Once you get all the information from the process, you can go and graph it. So steps 1 through really 7, they have you check symmetry. This one, if my function f of minus x equals f of x, I have an even function. And if f of minus x equals minus f of x, I have an odd function. If I have an even function, I know it's symmetric about the y-axis, right? An even function means that if I fold it over the y-axis, it's an exact copy of it. So this is just kind of nice to get more information, to say, if you know you have an even function, then your critical points have to match up. So if I have a critical point at 2, I also have a critical point at minus 2. If I have a horizontal asymptote at 8, I have a horizontal asymptote at minus 8. Vertical, sorry, my vertical asymptotes. If my horizontal asymptote's at 4, when I fold that over, I have to have a horizontal asymptote at 4 at minus infinity and positive infinity. The odd function is symmetric about the origin. So if I go to infinity on one side, I'm going to go to minus infinity on the other side. So we can kind of, if I have a critical point at 2, I'm going to have a critical point at minus 2. One might be a maximum, one might be a minimum type thing. So we have symmetry here is with the y-axis, and the symmetry here is about the origin. If you don't do this step, that doesn't mean anything. Sometimes it just clarifies that, oh, it's even, it's going to be symmetric about the y-axis, and you can clarify as you go that your critical points have to be plus or minus. Intercepts. You've probably done this in college algebra. Find the x-intercepts and find the y-intercepts of the graph. So I want to find the x-intercepts. There can be more than one. To find the x-intercepts, I solve for when f of x equals 0. And they're in the form some point, comma 0, because they're on the x-axis. The y-intercept, there's only one because I have a function, is going to be when I plug in 0 to my function, what do I get out? So my point would be 0, comma f of 0. There's only one. Another step in the process would be vertical asymptotes. Vertical asymptotes are going to be when q of x equals 0. The functions aren't going to be defined at that point, right? You guys have done vertical asymptotes in college algebra, pre-calculus, so there's nothing new there. Another step would be horizontal asymptotes. In calculus, we call this the end behavior. So to find that, I take the limit as x goes to infinity of the function, and then I also look at the limit as x goes to minus infinity of the function. If this equals L, this is your horizontal asymptote, right? So nothing's new. You guys done all this before, right? You find x-intercept. You've graphed rational expressions before. You find the x-intercepts, you find the y-intercepts, you find the vertical asymptotes, you find the horizontal asymptotes. So the new thing on it is going to be knowing when the function's increasing, when the function's decreasing, and then when the function's concave up and when the function's concave down. And that really has to do with the calculus. Your book also talks about the sign of the function. An important thing to note about the sign of the function, you have to take the interval, which includes the x-intercepts as well as the vertical asymptotes. So you want to look at the open intervals that has the x-intercepts and the vertical asymptotes. Those are possible turnaround points, right? If I have, you guys have seen graphs of rational expressions before. I might have something that looks like this, and I might be above the x-axis here and below the x-axis here, right? So if this is an x-intercept, let's go ahead and say this is an x-intercept. So if you only take into account the x-intercept, and if you plug in a point within this interval, if I plug in a point closer to this x-intercept, I get a positive. And if I plug in one on this side, I get a negative. So you also have to keep in mind your vertical asymptotes would be intervals. So in this interval, my function's above the x-axis. In this interval, my function's below the x-axis. My turnaround points for my function can only be for my above the x-axis or below it. Sorry, I shouldn't use turnaround points. The sign of my function, the only chance it has to change sign is when it crosses the x-axis or when it crosses a vertical asymptote on the other side of vertical asymptote. Here it's positive, here it's negative, but I didn't cross the x-axis. So I also have to take into account those points. I'm going to have to take in account those points when I do the first derivative test as well, and when I do the second derivative test. Because here I'm positive, and here I'm positive, but I could have easily been something like this, where here I'm positive and here I'm negative. But I don't have a maximum or a minimum. So I have to take in this account. The function's undefined here, so it's not in the domain. But I still have to test points on both sides of it to see if, does that make sense? And once I take an example of taking the derivative, I think you're going to see it a little bit more easily. Okay, so we've talked about x-intercepts, y-intercepts, vertical asymptotes, horizontal asymptote, and the sign of the function. And then we're going to talk about the derivatives. So f prime of x and f double prime of x. So when's it positive? When's the slope positive? When's the slope negative? When's it concave up? When's it concave down? Once I've done all this and I get the layout of my graph, I can graph it. So then the last step is to graph. 6. 7 is to graph. So let's look at an example of applying this. We're going to ask to graph the function f of x equals 2x squared minus 8 over x squared minus 16. We can do it in any order. So as long as we do all the steps, we're going to get the information to be able to graph it. So we want to make sure that we have no factors in common. If I factor this squared minus 4, here I have x minus 4x plus 4. If I factor it one more, I have 2x minus 2, x plus 2 over x minus 4, x plus 4. So no common factors. So that's good. Because if we had common factors, we'd factor out and graph the polynomial. Graph what's the rational expression that's left. So we can check symmetry. Am I going to have any symmetries here? Is this an odd function or an even function? It's even. So it's symmetric about the y-axis. So that's something I want to test as I go about. So if I know one side of the y-axis, I automatically know the other because the symmetry is with respect to the y-axis. Right? I can test that by plugging in minus x and I get out f of x, which clearly you see that, right? If I plug in minus x and I square it, I get x squared. And so I get the original function back.
That's how you find out if it's
Symmetric, if it's an even function. If all your powers of x are odd, then you have an odd function. If all your powers of x are even, you have an even function. If you have some mixture, then you have neither an even or odd function.
so every time you just plug in negative x for all of them, and then
Mhm.
you got the same, it's even, you got negative.
It's odd, yes.
You're talking about the exponent, right? It's going to be the exponent of x
Yeah.
squared. 2 is an even number, so.
Well,
it's-
yeah. So here, it's if I plug in a negative number and I square it, I get out what I
Yeah.
originally got. And if I do that, so this whole thing's not going to change if I plug it. Because negative squared is going to be negative. If this was cubed and this was cubed,
It'd be needed though, right?
it would still be even. Because negative x cubed is negative x cubed. And this would be negative x cubed, and I could factor that out and simplify it, and the negatives would cancel, so it'd still be even. If I had like this x cubed and this x squared, it would be neither. So if you have if all the powers of x are even, or if they're all odd, and you have more than one, you've got to be a little careful. Because if I just had x cubed is odd, but x cubed over x squared is just x, which is still so it gets a little more complicated. If you plug it in, you can clearly see it. So making conclusions of specific cases doesn't always make it true. So in this case, if this had a 16x, it would throw it off. So you have to just be a little careful. This one's even. X-intercepts. What are my x-intercepts? What are my x-intercepts? 2? Plus or minus 2, right? Because that's when the numerator equals 0. So that's going to be plus or minus 2. So that looks like x equals 2, y equals 0, and x equals minus 2, y equals 0. Those are the points on the graph, right? My y-intercepts. What are my y-intercepts? There's only one. What is my y-intercept? I plug in 0 to my function. What is f of 0? What is it? It's just right there. Is it 5? 1/2. Yes, okay. You guys are killing me. So the x-intercept 0 and the y-intercept, or sorry, the x point of this is 0 and the y point's 1/2. So if I was to go and graph this, I already know the x-intercepts and I already know the y-intercept. I know it's symmetric, so this definitely makes sense, right? That I have a plus or minus 2. Horizontal asymptote. So
Sorry, why are the x-intercepts only worried about the top.
Yeah, because the x-intercept's where I cross the x-axis. I will get to the vertical asymptotes, that's where I worry about the bottom. And that's where my function doesn't even exist at. Right?
So like the F0, I don't know.
This means I plug 0 into the function. That tells me I cross the y-axis, right? Because the y-axis is when x equals 0. So horizontal asymptotes, the end behavior. What's the limit as x goes to infinity of the function? Infinity. Is it infinity? It's 2. It's infinity over infinity. Apply L'Hopital's rule. I would get 2. Or you could say, from college algebra, the exponent is the power of x in the numerator is the same as the power of x in the denominator. So if I take the limit, it's a over b, which would be 2. And then the limit at minus infinity is also 2. So that tells me I have a horizontal asymptote at 2. It means my function is going to approach 2 as I go to infinity, and it's going to approach 2 as I go to minus infinity. But I don't know if it's approaching it concave up or concave down. So we're going to have to do a little bit more work. What about the vertical asymptotes? Very good. So that's when q of x equals 0. That's when x equals plus or minus 4. So when I plug in 4, my function's undefined. So I have a vertical asymptote there. So the sign of the function, just tells me where my function is above the x-axis and where is it below the x-axis. What are going to be my intervals that I have to include? What are my points I have to break up the interval in? Definitely 2 and minus 2, right? Because I'm crossing the x-axis there. Or potentially not. And 4 and minus 4, right? Because I can have some crazy jump on a vertical asymptote that I don't take an account for. So now if I get the function, if I plug in a negative, so let's take this function, let's just write it down here. Now I need to test the points, just like I do with my derivative and my second derivative. If I plug in, let's say I plug in negative 5. Negative, 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 negative. Negative times a negative divided by a negative times a negative is positive. So the function's above the x-axis here. Let's say I plug in minus 3. I have negative, 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 positive. Negative times a negative is positive, and it divided by a negative times a positive would be negative, right? Do you guys understand where that's coming from? If I plug in 0, I already know it's positive because I know it's a half. If I plug in 3, I have positive, positive, negative, positive. So we're all negative. And if I plug in 5, I have positive, 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 positive. Positive. Question?
I just had a question about the
Intercepts?
Well, just because it's like when f of x equals 0, is
Yes.
it actually p of x?
It is p of x more so, but it's when the whole function equals 0. The whole function equals 0 when the numerator equals 0. And that's another important thing. We have no common factors. Because if the numerator equals 0 and the denominator equals 0, we have a problem. Right? So if I plug in 0 to the numerator, then if I also plugged it into the denominator and got 0, then that would mean I have a common factor. So that's why you can just think of it as p of x equaling 0. Because 0 over 5 is 0. But we have a problem when we have 5 over 0, and that's going to be a vertical asymptote. So yeah, you can make that conclusion there. You would just have to be just a little careful to make sure it's not a 0 of the denominator. One way to do that is to make sure it doesn't have a common factor. Okay, so we got the sign of the function. Everything up until this point is algebra, college algebra level. Now we do the derivatives, and that's where the calculus comes in. So the first derivative of the function, so I'm not going to have too much time, but you guys should be able to do this on your own. Right? It's the quotient rule. The derivative of the top, hold the bottom, minus the derivative of the bottom, hold the top, over the bottom squared. Simplify that, I get this expression. right? So what are my critical points of my derivative? So when does this equal 0? When x equals 0, right? So what are the points I'm going to test on my derivative, my first derivative? Definitely 0, but what other points? Plus or minus 4, right? So doing the first derivative test is going to give me if this is a maximum or minimum, but it's also going to give me information about the function increasing or decreasing on the other side of this vertical asymptote. The second derivative, again, if I had time, I could go through this, but it turns out it's 48, 16 plus 3x squared over x squared minus 16 cubed. This never equals 0. The numerator never equals 0, right? If I was trying to solve for when this equals 0, 3x squared equals minus 16, that never happens. So this never equals 0. So where do I test my critical points in my second derivative? Does negative 4 and 4. That's very important because the sign of my denominator changes. The numerator is always positive, right? I take a positive number plus a number squared. Doesn't matter if it's positive or negative, it's always positive. But the denominator is going to change sign depending on those vertical asymptotes. So if I test some points in here, if I plug in negative 5, I have positive, positive. The denominator here is always positive because it's squared. So if I plug in negative 5, I have positive. If I plug in negative 3, I have positive. If I plug in a positive number, I have negative, I have negative. Right?
About after like the vertical asymptotes.
Yeah.
What is I'm confused about the second derivative.
The second derivative, what we're doing here, or we're trying to find if it's concave up or concave down.
Right.
So why we have to check it at plus or minus 4?
Yeah.
The reason why we have to check it at plus or minus 4, because if I plug in 0, I get a negative number cubed, which is a negative number. But if I plug in negative 5, this is positive. So it changes sign at a vertical asymptote. You always hold your vertical asymptotes in anything you do because your function can change without necessarily going through the x-axis, right? I know we have like a minute left, but if I plug in here, like I said, the numerator is always positive here. So if I plug in negative 5 squared is 25 minus 16, which is a positive number cubed is a positive number. So this is positive and this is positive, and here it's negative. Which makes sense, right? Because here I have positive and I have negative, which tells me this is a maximum. If I plug in 0, it means I'm concave down, which tells me again that point is a maximum. So putting all this together, I can graph this function. So if I go to graph this function, I know that I have a horizontal tangent at y equals 2. I have a vertical tangent at plus or minus 4. I know my x-axis. I go through my x-axis at plus or minus 2, and I go through the y-axis at y equals a half. X equals a half, sorry. X equals 0, y equals a half. So now I need to figure out what's going on here. From minus infinity to 4, I'm increasing in concave up, and I can never go through the x-axis. So that means I'm increasing concave up, and I am approaching 4. So the graph of the function has to be like that. I can't go below it, right? Because I know I'm concave up. And I cannot cross the x-axis, and I have to approach So I know my function's concave up, so I have a function that is like this. And I know I have to approach 4, 2, y equals 2, so this is my only choice. You guys see that? Here, clearly, this is my choice. I have to connect these 3 dots. I'm concave down here, and this is a maximum, so that verifies that. I'm symmetric about the y-axis, and I look like that. So now you can get information from the function from the graph. What is the domain of the function? All real numbers except plus or minus 4, right? What is the range of the function? All real numbers except the numbers in between here, right? More so, right? So 2 definitely is not in it, but also from open minus 1/2 to open 2 is not in the function. Or sorry, positive 1/2 to 2 is not in the function. All right, we will talk more about this section on tomorrow and take our quiz. Sorry to keep you a minute over.